Chapter 4.7 is on optimization. Now, what is optimization? What does that mean even in terms of regular English? So when we're optimizing something, we're basically making the most out of a situation. We're making the most out of a situation given whatever situation we're given, right? So mathematically speaking, we're typically minimizing or maximizing a situation. So whether you're maximizing the amount of area that you can have or minimizing the cost of building something, right? We are optimizing a certain situation. So let's take a look at example 1. It's the easiest way to look at it. Example 1 says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Well, first, make something of the situation. What do we have here? Build a diagram. 90% of the time, it really helps. You have some sort of a straight river, and a farmer wants to build a fence that goes around it. It's got to be rectangular, and does not need to be any fencing alongside this river. So if it's going to be rectangular, these dimensions will be the same of x and x. This one can be different, so we will call it y. The second thing you're going to do is find what it is, identify what it is that you are actually optimizing. Are you minimizing or maximizing here? Well, in this case, it's usually in the question, what are the dimensions of the field that has the largest area? So what we are wanting to do here is we want to maximize this area. So we want to maximize the area of a rectangle, which is going to be x times y. Now, the next thing to think about is what kinds of constraints do we have? Do we have unlimited fencing here? We don't. We only have 2,400 feet of fencing. That means this x plus this y plus this x can only be 2,400 feet. So 2x plus the y has to be 2,400 feet. Now what we're doing next is we're taking this area and we're going to use the constraint to write this area formula in terms of one variable. So this is what we're maximizing. So the area is going to be x times y, which we're going to solve for here, 2,400 minus 2x. So it'll be 2,400 minus 2x. So we now have the area in terms of one variable x, which is going to be 2,400x minus 2x squared. Okay? Well, and then the rest is easy. The rest is easy because when I have a formula for the area that varies with this x, I can actually find the maximum output. And that absolute maximum output is going to happen at a critical point, for example, when a prime here is 0. Right? So I'm going to find a prime, and you're going to find the maximum, the local maximum for x. Oh my goodness. 2,400 minus 4x. And then I'm going to solve for that when it's equal to 0. Add 4x, x is going to be equal to 600 feet. Right? Now, when testing for this, I am testing less than 600, greater than 600. But let's be honest here, this x does have a minimum value, as a minimum value of 0. It does have a maximum value. If all the way around is going to be 2,400 and x has to be split in 2, when y is 0, the maximum value has to be x is 1,200 here. So if you test out your a prime, in this case, between 0 and 600, your a prime is going to be positive. Between 600 and 1,200, your a prime is going to be negative. So it looks like your area will peak right here at x equals 600 feet. Okay, I put in number 6 for you because the sixth step is what a lot of people forget. It's not just to find what x is here, to find the maximum. The final question is, what are the dimensions of the field? So in this case, it would have to be 600 feet. Well, x equals 600 feet by y equals, well, if x is 600 here times 2, 1,200. 2400 minus 1200 is 1200 feet. So this would be your final answers. If you have a diagram, what variable is x and what variable is y is very clear, so you need no more than this. Okay. Now, example 2 is actually doing the same thing. It is asking you to, this time, you have a cylindrical can. It's holding 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Again, it's optimization, so you are making the most out of a given situation. We want it to hold the 1 liter of oil, making the most, meaning also we want to minimize the cost. Okay, so the diagram is basically going to be a cylindrical can here. It's going to be based upon a radius and a height. What is it that we're trying to minimize? We're trying to minimize the cost of the metal it takes to manufacture the can. Now, the metal part of this can is going to be equal to the surface area. And the surface area of a cylinder is going to be the area of the top, the area of the bottom, circles, which is 2 pi r squared, plus the area of that label, which if I were to cut this and open it way up, the height will be corresponding to the height of the can, and this width of this rectangle is going to correspond to the circumference of the circle, which is 2 pi r. 2 pi r times h will give me the area of this label right here. Right? So this is what we are trying to minimize. We're trying to minimize the area of this can, the surface area. Now, what is my constraint? My constraint is that the can itself has to hold 1 liter of oil. 1 liter of oil is the volume. So the volume has to be 1 liter. Now, the volume formula for a cylinder is the area of the base times the height. And in thinking of solving for R and H, we're going to convert 1 liter of oil to 1,000 centimeters cubed so that we can solve for the centimeters, for the radius and the height in terms of the centimeters. So now you're going to do the same thing. You're going to finish this problem by finding A in terms of one variable. And I would recommend you actually find it in terms of R. So I'm going to solve for H here and plug it in here. You're going to find the area in terms of R, and you're going to find the minimum value, the minimum area here. Okay, and we will go over those answers tomorrow in class. Moving on, I do want to move on to example 3 in the last few minutes that we have. Example 3 is a little bit different. It's less situational and more graphical. Okay, so let's take a look. Find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Well, let's see here. If we have a y squared equals 2x, what kind of a situation do we have? We have a horizontal parabola, it looks like. Yeah, that looks pretty good. And then you have a point that is 1, 4, which I will tell you right now is somewhere out here. Okay. What we want to do here is we want to find a point on this parabola that is the closest to this point 1, 4. And it's probably going to land somewhere around here. We don't know where it is. We don't know what that point is, so we're obviously just going to call that x and y. And what are we trying to optimize here? Okay, we're looking for the point, this point, that is closest to 1, 4. What is it that we are minimizing or maximizing? Well, essentially, we are minimizing the distance between these 2 points. Right? So if I call this D, I want to minimize this distance D. If you remember the distance formula between 2 points, it's the square root of x minus x1 squared plus y minus y1 squared. It's essentially your Pythagorean theorem. It's going to be, because it's a square, I'm going to do x minus 1 and then y minus 4. So x minus 1 squared plus y minus 4 squared. Right? We want to write this in terms of one variable. So what is my constraint? Well, our situation says that this is what my unknown is, this point right here, x, y. Can this x, y be anywhere? Can it be here? Can it be here, here? No, it cannot. Can't be just anywhere. The relationship between this x and y has to be on this parabola, meaning the relationship between this x and this y is this. So your constraint is the formula itself, y squared equals 2x. Now I want to write this formula again. Step 4 says to write the formula, what it is that you're trying to optimize. We're writing it in terms of one variable. The easiest one to solve for is x, so x will be y squared over 2. So d in terms of y, because I'll be replacing the x, is y squared over 2 minus 1 squared plus y minus 4, the whole thing squared. It looks pretty crazy, but in trying to optimize, so this would be step 4. So 1, 2, 3, this is step 4. Step 5 is to actually now optimize. Right? So I am going to take the derivative. And in 4 minutes, I'm going to do this pretty quickly. So 1 over 2, the derivative of this full outside. Right? And then I'm going to take the derivative of this inside function. So 2 times y squared over 2 minus 1 to the first power times the derivative of the inside, which is y, plus 2 times y minus 4, derivative of the inside is just y. We're looking for where this is equal to 0, where the numerator is equal to 0. The denominator, if you take a look, you have a perfect squared plus a perfect squared. When is that ever going to equal 0? It will never, because it will never cancel out to be 0. So we're really looking for where this, let's take a look, 2y plus 2y minus 4, when that equals to 0. Well, let's take this out and take a look. We have y cubed over 2 minus y plus y minus 4. Nicely done. 4 is equal to y cubed over 2. Y cubed will equal to 8. Y will equal to only positive 2. So at y equals positive 2, it looks like if you test it, you will get, so y is equal to 2. Is there a minimum value of y? Nope. So if I plug in 0 into, where is it? This formula, it'll become positive. Where is it? 0, negative, 0, minus, minus. So this will be negative. And then this will be positive if it's greater than 2. So then it will become a minimum value. So this would be d prime and d. You'll have a minimum distance at y equals 2. So the final answer would be when y is equal to 2. And if y is equal to 2, right here, you'll get 4 is equal to 2x. So x will equal to 2 as well. At 2, 2 will give you the minimum distance. So this will be 2, 2. Right? We only have 50 seconds left. So this is, I'm going to get you started. Find the area of the largest rectangle. You are going to be doing this. The picture is a semicircle that looks like this. And you are optimizing the area of this rectangle. This point is x, y. This is x. This is y. Try that, finish it, and I will see you tomorrow.